Hello, everyone. Welcome back to Fabric Espresso YouTube channel. And this is a series about data engineering and data science. Today, we have a special guest who is joining us directly from the engineering product group, Karuna. Thanks, Karuna, for joining us.
Thank you. Thank you, Estera.
Can you take a moment and introduce yourself and tell us more about what items, what areas of Fabric you are working on?
Yeah. So, as you know, my name is Karuna, and I've been in the data engineering team for the last 3 years now. And I've been working on a bunch of things. So, off late, recently, I've been working on workload optimization, or what we are calling as Autotune feature. This is a feature where we are trying to optimize Spark configurations automatically on behalf of the customer, so that we can get better performance out of it.
Awesome. Thanks for setting the stage. So now we can jump into the discussion. So the topic for today is to discuss Autotune for Apache Spark configuration, or from the other side, I would suggest the name, Predictive Optimization for Apache Spark Jobs. Karuna, would you agree with naming Autotune as Predictive Optimization?
Yeah, I think so. It sounds like the right name. Yeah, we are trying to be predictive about it, and there is a bunch of optimizations going on for the Spark jobs. Yes, sounds right.
Awesome. Let's start again. Today I'm going to present because that's another feature that I'm the feature product manager accountable for, as well as Spark runtime and native execution engine that we have talked a few episodes ago. Now let's talk about the real need coming from our customers. We asked our customers, how often do they tune Spark settings? Karuna, how many Spark settings do we have as of now? And what is Spark setting?
So, firstly, Spark settings are a bunch of configurations. Basically, these are knobs. As a Spark developer that can tune or push around these knobs to get different effects. For example, you can configure the number of cores that you want, the number of memory you want, amount of memory you want, the number of executors you want, the broadcast threshold, and so on and so forth. I think on Spark 3, there are about like 300 to 400 Spark configurations. And looking back, the number of Spark configurations have been increasing as more features land on Spark. So yeah, there are about 300 Spark configurations.
That again, every Spark expert can optimize, and we can optimize those Spark configs for every job, for every query. At the same time, we ship Spark as part of our runtime, as heart of our runtime. We have also Delta Lake, and Delta Lake is coming with additional few hundreds of Delta settings. But eventually, the reality is that again, if you are using Apache Spark big data processing platform, there are so many different elements that you can tune. And it's challenging, it's time consuming, and it's money consuming. Because to find the optimal Spark setting, you need to run experiments because it varies from the query, what kind of query have you created. It varies from the how many number of rows you are accessing. So it's very challenging to make sure that the Spark settings are set correctly. And that was the need that we started from. The need is that we all want to make using Apache Spark simple. If you agree with that statement, please leave the like or the heart under inside the comment section. As again, we hear you, and we also believe so that configuring Apache Spark for optimal performance should be easy, it should work out of the box. And that was the need that pushed us to, first of all, investigate the research idea, and then for the few years of creating an option to automatically provide the ML-based predictions which are optimizing your Apache Spark jobs, your Apache Spark engine. So first of all, let's start with a demo. Setting up Spark for optimal performance, it's tough, but should be easy. That's why we made Autotune. Now, we are going to see how everyone can reduce job execution times thanks to the automatic AI-based intuition built into our Spark runtime. I already have a notebook for which I enabled our unique feature, Autotune, just by running a single cell with the flag Spark MS Autotune enabled set to true. Then I wrote a query which runs some aggregations and process big data. Imagine this query is part of the bronze to silver layer, or maybe to gold as well. Now, let's schedule the notebook to run every 10 minutes, as Autotune targets repetitive queries. Let's take a look at the historic runs to see the execution time. Let's go to Monitor Run Series, and thanks to the feature name Recurrent Job Analysis, we can see the full metrics for the previous run of the same query. As you can see on the chart, we started with the execution time around 8 minutes. This is not a simple query and it processes billions of rows. When a Spark query is executed, Autotune generates a tailored ML model for that specific query. This model is designed to understand and optimize the query's execution by analyzing patterns. Autotune configures 3 Spark settings for each of your query separately. It configures the number of partitions to use when shuffling data for joins or aggregations. It configures the maximum size in bytes for a table that is broadcasted to all worker nodes. Autotune defines the maximum number of bytes to pack into a single partition when reading files. To recap, Autotune automatically adjusts Apache Spark configurations to minimize workload execution time and optimize overall performance. This feature empowers you to achieve greater efficiency with fewer resources. And the best part, as of now, Autotune is available in all regions, so you can easily enable it for all your Spark notebooks and jobs. Let's talk about the case study coming from one of our customers. So first of all, we asked the customer during the early preview stage, that customer was part of early adopter or private preview program, to run all the queries inside the notebook without Autotune. And then we asked the customer, okay, now enable Autotune because at least we have a point to compare the past performance with the current that will be optimized by Autotune. As you can see on the screen, at the beginning, the performance varies. And then after the first run, the performance drastically drops. So we started with a little more than 500 seconds. And then the performance with Autotune enabled dropped to the level of 350. Now, Karuna, can you tell us a little more what happened during the first 5 iterations?
So Autotune is continuously listening to your queries and we are trying to learn from it. In this particular case, the first time we see the query, we really have no clue what this particular query is. We run it with the default configurations. We really can't do much at that particular point. Subsequently, we start collecting information about the query. And each time we collect this information, we are training a model specific to that particular query. And these models kind of get better and better over a period of time. So the first few iterations that you see, the first few times that the query is running, we are learning from it. And as we are learning from it, we get better. That's what you see. And the performance drops because our models are getting better. We reach a stage and you can see after about 15th iteration, or maybe say 20th iteration, performance gain kind of plateaus. And that's because there's only so much that you can tune and the machine learning models have kind of reached a limit. So that's what you kind of see in this particular graph that's going on.
Great, that makes sense, and we'll dig into the ML behind the Autotune. I want to make a point that we built ML model for each query. So each query is optimized separately.
Yes, that is correct. Yes, each of these models are optimized separately.
Now let's talk more about the use cases when we think that our customers, the users of Microsoft Fabric, data science and data engineering, they should consider enabling Autotune. So first of all, we have 3 qualifiers. The first is when you have repetitive queries. So every query that you run based on specific predefined frequency. For example, every hour, every day, every week, every 5 minutes, or every minute. If you have a repetitive queries, so ideal ETL workloads. ETL workloads are about the repetitive practice of moving your data, transforming your data, then Autotune will help. Secondly, when you have long-running queries. So the long-running queries are queries that we defined that takes more than 15 seconds. And why 15 seconds? Because again, the nature of Apache Spark and JVM processing is that there is always small noise. And if the query takes 5 seconds, and if we will add the gain coming from Autotune, that the query is going to be optimized by 30%, because that's our objective, then the impact is not visible. If the query takes more than 15 seconds, ideally a few minutes, up to like multiple minutes, like 40, more than 40 minutes, we can see lots of those queries running on our infrastructure. Then the impact of Autotune, which I will repeat myself, the objective is to bring the 30%, around 30% of the performance boost. So then the impact is visible. And the third item, there are 4 languages that you can use to author the query in Apache Spark. First of all, Scala language. Secondly, PySpark. So Spark for Python. Third is R. And the last one, Spark SQL. Now, if you author the query, then it's going to be translated to the engine. The logical, then physical plan is going to be built. And in 95% of the cases, again, based on what I've seen, 99% of the cases, the query is aligned with Spark SQL API, and Autotune is going to accelerate the query. There are some brave customers who are authoring the queries based on RDD API. First of all, it's super challenge and super rare to author the query in RDD API. That's why I'm just mentioning that in 99.9 cases, Autotune will work for your query. The only case it will not work is if the query has been aligned with the RDD API. And then whenever you are using Parquet or Delta Lake format, data format, Autotune will work for your query. So to recap, when you read the data, process it, you do joins, explanatory data analysis, and if the query takes more than 15 seconds, and if the job is repetitive, so a notebook, for example, is scheduled, then it's a perfect case for Autotune. So I would say all ETL cases are perfect cases for Autotunes. Karuna, would you like to add anything? Have I covered all the cases, or there is something that needs to be commented?
You've pretty much covered the entire thing. So I just like to reiterate. So saying that these are repetitive queries, long-running queries, and the Spark SQL. And Autotune automatically looks for such kind of queries and tunes them. So as a customer or as a user, you don't really have to look for such kind of queries and enable Autotune accordingly. So this is all happening behind the scenes for you. These are things that you don't have to take care to enable Autotune.
To add a small clarification, Autotune is available in all production regions. So for all our Fabric users, we are just encouraging you to enable it. Once you enable Autotune, Autotune will check for all those qualifiers. But I want to reiterate that Autotune is disabled by default. This is a feature that you can enable for your notebook, for your jobs, and we'll talk more how to enable it in a few seconds. Now, I would like to discuss the technical details of Apache Spark architecture and where exactly the innovation Autotune is headed. Karuna, over to you.
Thanks, Estera. So this diagram, I think you guys have seen this particular diagram as a Spark SQL processing. How does a workflow happen? So not going through the details, you start with a Spark SQL text and it goes through various phases before it gets executed. So one of them is you convert this into a logical plan, a tree, and use a catalog to kind of do some analysis on it. And then we generate something called a logical plan. We optimize the logical plan using a bunch of rules and then generate a bunch of planning physical plans, or this is called the planning stage. One of these plans is selected and we send it down to the query execution layer, which actually takes this particular queries or the plan and executes on different executors. So coming back to Autotune here specifically sits in between the optimized logical plan and the physical planning steps. So once we finish the optimized logical plan, we use this particular plan to figure out what is the best configurations, inject those configurations into the plan, and then proceed with physical planning and query execution. So now that you've seen where Autotune kind of fits into the query execution planning and execution, so this is a high-level architecture diagram of Autotune. So what we have here is something called as a Spark core workload on the top. We have the Spark cluster to the bottom right and the Autotune backend on the bottom left. So as a user, when you come into Fabric and you start off a notebook or submit a Spark job definition, all of these requests essentially land up on what we call a Spark core workload, and specifically a component called a Strident job service that is shown in the yellow at the top. So the try and job service has a bunch of responsibilities. One of them is it ends up submitting a job to the Spark cluster. So this is what you see on the bottom right part of the screen. And as you know, the Spark cluster is made up of a driver and a bunch of executors. There are two specific components of interest for Autotune, and these are sitting inside the driver. One is called as the Autotune config inference, and the other one is the Autotune query listener. So in the previous slide, when we talked about saying that after the logical optimization, that's when we kind of look at the models, machine learning models that we have learned, do some inference and inject those configurations. And this is exactly what the Autotune config inference module is responsible for. And all of this is happening inside the driver. So that's why this particular module is inside the driver. And then we inject the best configuration that we can suggest at the moment, do the physical planning, generate the RDDs, do the query execution. These executions happen on the executors, and once you have the query execution completed, we collect information about this particular query run, specifically using the query listener mechanism that Spark provides. So the query listener selects a bunch of features or details about the particular query and sends it out as an event or an Autotune event to the Autotune backend. You can see that we end up writing events to the storage accounts, the event storage accounts. Looking at the Autotune backend, we have an event grid and an event help mechanism to kind of trigger the model training based on the events that are coming in from the query listener. So we use Synapse Spark to run the machine learning and store these events in a database. So once we have this machine learning models trained, we serialize them into a Onyx file and store these Onyx files on the model storage accounts. So that's on the topmost storage account that you see here. And these storage accounts was accessed by the config inference module to do the inference and inject those configurations during after the optimized logical planning step. This is a feedback loop that keeps running over and over again, and we kind of get better over a period of time. So the interaction between the Spark cluster and the Spark core workload is we need to get these SAS URLs to the storage accounts. And we want to make sure that these SAS URLs are secure, and also at the same time, we make sure that we have privacy compliance. To address the security, so these SAS URLs are scoped down to a particular job, to a particular artifact, and the Autotune manager inside the Spark core workload is responsible for ensuring this. So the Spark driver invokes Autotune manager, asks for a SAS URL. The Autotune manager does a bunch of authentication, authorization, and verifications before it hands out the SAS URLs to the Spark cluster. There's also a refresh mechanism because we don't want the SAS URLs to be long-lived. There are two different SAS URLs that you get, one for the model storage and the other one for event storage, and they're scoped on with the right permissions and the right folder paths. So the query listener is collecting a bunch of features. And these are features we want to make sure that we are privacy compliant at the same time, along with the security that we just talked about. Now let's talk about the machine learning features that we collect in the query listener. This is what we also call as the Autotune events. And here is an example of an Autotune event that we are collecting. This is just an example with some dummy values, but what's more important is the kind of information that we collect. So to begin with, we have something called as a query signature. The query signature is essentially a unique way for us to identify a particular query. And this is how we identify individual queries and kind of look up the corresponding machine learning model from the storage accounts. So the query signature is essentially a huge number, but this number is essentially a hash that was generated of the logical plan that we receive. When we generate these plans, we make sure that we have privacy aware and we don't include any PII or EU PII information, kind of strip away many of those set of information to generate the query strings, query signature. And then next we have something called as the features, or what you see on the screen. And these are features of the query features. So again, we don't want to collect the entire plan and information about the plan or any data to avoid security and privacy concerns. So we are just collecting information about the shape of the query. Things like how many aggregates do you have, how many joins do you have, how many filters do you have, and so on and so forth. We also collect information about the size of the data, how many records are we operating on, how many megabytes or kilobytes that we are operating on, and so forth. So these are all information that is used to train the machine learning model. The other set of information that we collect is what's the Spark configurations that this particular query execution ran on. So we collect information about the max partition bytes, Autotune broadcast threshold, how many executors were there, the memory size, hop heap size, and a bunch of other Spark configurations that are of interest. We also collect how long did the query take, the duration in milliseconds, And every event is stamped with a unique identifier so that we can use this for our debuggability and traceability.
That's phenomenal. Now let's talk about AI-based intuition that is behind Autotune. And here I will invite Yiwen, the data scientist that has been with us working on Autotune for the last few years.
Hi everyone, this is Yiwen. I'm a data scientist, and my focus is on the development and evaluation of the Autotune algorithm. So the intuition behind the Autotune algorithm is as follows. We start from a relatively good default that has been manually tuned by a lot of experts, and we leverage a machine learning model to fit a surface, like you see on the top right-hand side, a surface with respect to the different configuration settings, what is a good or bad configuration. And then we will leverage this model to suggest the optimal configuration. And then we actually test it or execute a query with the suggested configuration. And then we repeat this process and achieve a better improvement of the performance over time. So in the approach, we also introduce an innovative ideas of leverage offline experiment exploration phase using benchmark workloads to enrich the knowledge of this machine learning model. And during the online phase, we will do the fine tuning such that the model has better and better performance of the customer query over time. So let me dive into more details of this process. So the user will first submit a query, and with that, we fetch the machine learning models that we store in our storage to optimize the configurations. Specifically, we generate config candidates around the current Centroid, which is the default config as a start. So we will pick the one that has the best machine learning prediction, and we set the config for the customer. And upon finishing of this query execution, this record of perf config tuple will be added to our database. We then update the machine learning models with this new observation, and we will update our Centroid as well. So in that, we hope that the machine learning model will gain more knowledge about this particular customer query being fine-tuned, and the Centroid will also move towards the great direction to further improve the performance. And we run this process iteratively to achieve improved performance over time. And as the candidates are always generated around the Centroid, not so super far away, so we effectively reduce the likelihood of a significant performance regression to be more conservative in our tuning process. So let's talk about a bit more on the Centroid update, which is our secret sauce of this algorithm to make it more robust. So the goal of the Centroid update is to guide the Centroid to move towards a better area gradually, and it consists of two main steps. The first one is we want to find the best candidate in the previous observations we have seen so far. And based on that, we find the gradient we want to descend towards, meaning that for each configuration dimension, such as shuffle partition, which one is the direction we want the Centroid to descend or increase, decrease to. And compare with the previous model, for instance, they sometimes look at two observations. One configuration is smaller, one is larger. What is the performance comparison? They just leverage those two observations and determine the gradient. In our method, we extend it to leverage all the points and feed a curve to learn the trends that significantly reduce the impact due to the noises. For instance, based on all the points, we can look at what is the trend of the configuration change with the impact on the performance. And we can make the algorithm more robust. And to consider the change of data size, we also introduce the more dimension about data size to monitor what is the normalized performance of each candidate, and then learn the trend after reduce the impact of data size change. So that is how we tackle the two challenges and make the performance more robust. And talking about the responsible AI aspect, we first develop a transparency note that can be used to fully inform our users about this Autotune feature. The intent is to reduce the misunderstanding about the feature and inform the user about the potential use of the data and inform them about the potential benefits. And at the beginning of our architecture design, we also went through a very comprehensive review for both security and privacy to ensure that we are well protected under any protection attack and manage the customer data properly following the strict data compliance standard of Microsoft. And upon the launching of the feature, we have been working very hardly on improving our dashboard to monitor the system, creating alerts for any abnormal behaviors, failures, and observe the performance impacts, etc.
This is the moment that I want to talk about how to enable Autotune. In the meantime, this is a similar case as for native execution engine. We are working on enabling the UI, we are working on adding a toggle button that will simplify the way how you can enable Autotune. As of now, you can enable Autotune by following two ways. First of all, you can enable Autotune for a single notebook or a single Spark job definition if you will just add one simple Spark setting that will set Autotune enabled to true. If you use an environment item, you can enable Autotune for all items that are associated with the environment. Just add a Spark property, so Spark setting, the same as for individual notebook, so Spark MS Autotune enable set to true. And that's it. In that case, all the jobs, all the notebooks associated with the environment will inherit that setting. We have also added the integration with logs and monitoring. So you can go to your driver logs, type bracket Autotune, close the bracket, and you will find logs coming from Autotune feature. Logs about if the query has been qualified to be optimized, to be boosted by Autotune, what are the Spark settings that Autotune applied for your query, and all the information about Autotune related for your query. Then we have also added the integration with Run Serious Job Analysis. The episode has been published a few weeks ago on our YouTube channel. Now I'm just mentioning that for your jobs, you should see the pattern that the execution time is going down thanks to the integration with Run Serious Job Analysis. And that's all what we prepared for today. I can mention that Autotune is in a preview stage. In the meantime, we are working on making that ready for GA, but the bar for GA features in Fabric, we are setting high security, reliability, and the performance impact. I would love to hear from you, from our users, from our customers, what boost you can observe. I want to mention that right now Autotune works for two runtimes, 1.1 and 1.2. Feel free to reach out to us through the comment section or directly to the social media channel and share the perspective and the boost that Autotune brings for your jobs. Remember to hit the like button, subscribe the channel, and until the next time, happy exploring Autotune predictive optimization for your Spark jobs. Karuna, thanks for joining and see you again.
Thank you, Estera. Bye.